So we're just a couple minutes in. We got to start the recording. Just talking about the delta S works the same as delta H. So what are you going to do? And I just wanted to get the idea that you're going to do what with these two, and then subtract the reactants. So these two added together minus the reactants. So that is 251.9, is that right? Okay, so the entropy change here is a positive 141.9 joules per mole K. What does that tell us? What does it tell us here? Thinking about the positive specifically, what does it tell us? Just tell us first. Something with entropy. Something with entropy, good. All right, somebody help him out. Maybe. It won't tell us the whole story on spontaneity, but it helps to answer the question. Okay, but what does it tell us about the entropy specific of the products versus the reactants?
Oh, there's more entropy on the products than on reactants.
So when this reaction happens, it increases the entropy in our system. Okay, and remember I said that the key to this is defining our system versus our surroundings. Okay, this tells us about the entropy in our system. Okay, good, make sense? I'm going to go on. I'm not going to do all these in the sake of time here. Now, our second law of thermodynamics. This is the one we're focusing on here. Now, reading that through, I mean, it's written in science language, right? But what does this tell you? What does the second law tell us? The entropy's got to increase. Everything that happens in our universe increases the overall entropy of the universe. Everything we do, right? You have to be careful, you're going to get into who's on. Pink Floyd's on, but everything under the sun increases the entropy, right? So, well, if everything tends to increase the entropy, Carson, maybe we can use that idea to sneak up on your question of spontaneity. If it's spontaneous, it should increase the entropy of the universe. If it's non-spontaneous, it doesn't, right? So if we could just measure, if we just had an entropy measurer, we don't. Okay, so if we had an entropy measurer, if we could just measure the entropy of the entire universe, and then do a reaction and measure the entropy of the entire universe again, right? We would see whether the entropy of the universe increased or decreased. Obviously, it's a foolish errand. There's no way to access the entire universe at one time, right? Other reactions will be going on at the same time to complicate things. There's lots of problems, right? So we can't measure the entropy of the entire universe. So what could we do? How could we approach it? How can we approach this problem? So we need to know what reactions are spontaneous. We really, really need to know this because that's how we build bonds, right? An important thing, but okay. I'm sorry. We're listening to History of World War II on our commute, and that's why I'm thinking about how important it is to know how to build bonds, right? Okay. So how can we approach this problem? And we can't measure the entire universe, right? How can we do it? No ideas? That helps. What do you mean? Okay, we'll get a measure. I can't measure yours. Measure the system. Okay, all right, cool. So first I'm going to measure the system. Maybe I could figure out a way to measure entropy changes inside the system, right? Okay, cool. But what else then do I need to do? Same thing like Chem1212. What did we do? What did we do Thermo into? The reaction in a styrofoam cup. Let the reaction happen. What do we measure? I don't have an energy measurer either, right? Well, could measure volume change, but that's more complicated than that. Temperature. So if I can watch the temperature change in the surroundings, I could talk about energy flow into or out of the system. I can measure the entropy change in the system, and I can measure the energy flow from the system to the surroundings. Those two things should give me goals. Does that make sense? So this is second law reduced to an equation that the delta S of the universe greater than zero. I think technically I should really be technically correct. It's probably better to say greater than or equal to. Make sense? I guess technically equal. But greater than the delta S of the universe for everything is going to be greater than or equal to zero, and also, importantly, the delta S of the universe can be defined as the delta S of our system plus the delta S of everything else. Okay? And that's the point. The surroundings here, the second term in that, the surroundings here we're going to define as everything else. So by definition, delta S of the universe has got to be the thing we're focused on plus all the stuff outside of the thing we're focused on. Right? We can't measure the whole universe. We could really carefully measure that one. This one, we've got to look at the energy flow, which is what we did in Chem1 with the delta H. Okay? So the delta H from the system is going to give us the surroundings part. Going to focus on right now, that's a plus. Okay? It's not going to be a little bit. I'll show you why. Okay? Okay, so there's our equation again. Ready for some algebra? I know how much y'all love the algebra, right? Here come to algebra. Okay, so the amount of heat that flows to the surroundings is the negative of the delta H of the system. Does that make any sense? So here's where my negative is coming from. I really care about the delta H going into the surroundings, but I can't measure it. All I can measure is the delta H coming from my system. That's why it's negative. That's why it's negative delta H that is exothermic. Okay? So, and also it's proportional to inverse temperature because it's harder to drive energies out to a hotter surroundings. Right? You have to heat up more. Does that make sense? So now we are at the delta S of the universe is the delta S of our system, still plus the delta S of the universe, but now at second term, delta S of the universe I've changed to minus delta H of my reaction that we did in Chem1 divided by the temperature. See what I did so far? Substituted that in. Now I'm going to play with the algebra a little bit, and I'm going to say I'm going to multiply everything by T. So I just multiply through by T on both sides, okay? It cancels out the T on the third term, the delta H divided by T. It's now just delta H because I multiplied everything by T. But now I've got temperature times the delta S of the universe is equal to temperature times the delta S of the system minus the delta H of the system. Does that make sense so far? Okay. Other step. Multiplying through by -1. Okay. Randomly multiplying through by -1. Now what have I done algebra-wise, y'all? What did I do? Split. Okay. Commutative property works. Okay. And I have this new system. Now after I flip this, right, this is the same. I left off the system here because the only delta S we can ever measure is the delta S of our system. We can never measure the delta S of the entire universe, right? So this delta S that we're talking about here in this equation is the delta S of our system. This is the delta H of our system, our reaction that we're looking at, right? Now we're going to hang a new term on it here, the negative T delta S of the universe. We're going to call this new term the delta G, or the reaction. It's named for Josiah Gibbs, the fellow's name. Over here in the States, we like to talk about Gibbs because he's like one of the first random chemistry people that has something named for him that's American. Because they all used to be German and stuff. So this guy was actually from here. I don't know where exactly, New York, I'm not sure. Okay? But we've got delta G now defined. This one does work. If to define the spontaneity. This is what it's I put a slide with nothing on it but the equation. That probably implies that it's an important equation to have, right? To be able to manipulate it. Like, see this one much, Allison? Do you see this equation very much?
I saw it a lot.
Okay, all right. Yeah, Kim, okay.
I think like first 3 weeks we spent a lot of time talking about this.
Yep. Well, you already know that. So good, you already know. Well, this is the Gibbs free energy, or simply the free energy we also often say, or just the delta G is actually how students say. Delta G of a reaction. And just the same as exothermic, we're going to say, remember, how do you define exothermic for reaction? Delta H is what? For exothermic. Negative. Negative delta H is exothermic. Products minus reactants. Okay. Well, same idea. Negative delta G is going to be spontaneous. Okay. Same idea. Make sense? If delta G is negative, spontaneous. Sounds easy, right? It gets more complicated. Of course it does, right? But if our delta G, this is what it says. I know, listening to this, delta G less than 0. It just means if it's negative, y'all, okay? If delta G is negative, it's spontaneous. If delta G is positive, it's non-spontaneous, but that just means we wrote it backwards. If delta G is positive, flip it around. It'll be negative if you run the other direction, right? And so it's spontaneous the other way around. If delta G is 0, that's called equilibrium. Because if delta G is negative, it's spontaneous. It's naturally going to go that direction. If delta G is positive, wait, it's going to go back the other direction. Oh, wait, but when it settles down and delta G is 0, that is by definition equilibrium. It's not going to go either direction. Remember, the reaction doesn't stop. It's just that the forward reaction rate is equal to the reverse reaction rate, and it's at dynamic equilibrium. Okay? Ready, Mercy? No, not ready. It is important, right? I mean, we're gonna ask this question and we're gonna hide this question a lot of times. We're gonna ask this question a lot of times. What's the delta G? What does that tell you? Right, when you see a question on an exam, it's like, calculate the delta G. Okay, what's this tell us? Well, these are the answers you're looking for. Does it tell me that this reaction, oh wait, delta G is negative? Okay, well, that means it's gonna go that direction. Or delta G 0, it's at equilibrium, whatever, okay? A negative delta H helps a delta G be negative, but it's not the only thing involved, right? And a positive delta H helps a delta G be positive, but again, it's not the only thing involved. Because there's that delta S, the equations up top there imply delta G equals delta H minus T delta S, right? And so now we've got to include both of these things. Exothermic or endothermic, yes, that matters. But then we got to take the temperature multiplied by the entropy change of our system, and then see what that does to the overall delta G value. Play with it a little bit. So here's the grid, okay? Just sketch out on your time. I'm not going to take it up or anything. I want you to sketch out here some delta G's, okay? So in the first case, what am I saying in the first column about delta H on the first line? What am I saying? Delta H is negative, meaning that this is an exothermic reaction, right? That right there tells us this is an exothermic reaction, right? You agree? Yes? Think about it. Random value for your delta H. Okay? Now, Kara, the delta S here is positive. Okay? So that means that my products have more entropy involved than my reactants. Okay? So my reaction actually increased entropy inside my system when it happened. Agreed? Okay, well then, is my reaction spontaneous or not? And how do we calculate, or how do we determine spontaneity for a reaction? Delta G. And on what values am I looking for? I see whether delta G is what? Okay, that's the whole key here. All right, so did you decide in this first case about your delta G? Given what equation? What's my equation? Delta G equals delta G equals delta H minus whatever temperature I chose. Use Kelvin, by the way. Temperature times the delta S. Well, so if I have a negative delta H minus what random temperature you want, Gary? 30K is really cold, but okay. 30K times a positive number, what's it going to do to my delta G? I have a negative minus 30 times a positive. What does that do? What? You see it at that, what is it? It has to be negative. There is no way for that value to not be negative. Does that make sense? Okay, so what are you going to put in the delta G column here? You're going to say that it is negative. Got to be, right? What are you going to put in the spontaneous question mark? That one's got to be spontaneous. You see how this exercise works? Okay, cool. Let's do line 2. Everybody do line 2 first. Talk about it with people if you want. Lori, what are your thoughts? You talk about it with people? I'll talk about it with people. I'll come back to you. All right, Lori, thoughts? Oh, wait, why, Kara? You're saying none. Let's see. Why? Delta H is positive. No temperature time. But the temperature times delta S, yes. Okay. So positive minus a negative is positive plus positive. It has to be positive. Makes sense? Thank you. Lori said thank you. All right, cool. All right, well, on to the next one. Have that. Y'all talk about it. Jared's up next. Think about it. I'll say you got next. Who's up, Kira? Hit somebody. Yeah, pick somebody randomly then. Pick somebody. You can be brave. It's okay. Like Carson said earlier, just make friends here.
Forgot it.
Well, point at somebody then. Close your eyes and point. Don't direct.
Here.
Yeah, I did. It's good for you. Mercy. All right, Mercy. What do you want to answer here? So we said in the first case, Murph said that it's negative, right? And Kiera said in the second case it's positive. What do you want to put here?
If we stay with the science that they have, it would be positive minus negative.
What? Y'all understand what she's saying? Maybe.
Values like.
Yes. Yes. Ah, you hit on it. Okay, so this one depends on the values involved in the reaction, but for that reaction, right? So my delta H is positive, right? If there's no T delta S term, well, we have a positive delta G. That's not spontaneous, right? But we do have a minus T delta S, right? So at a very, very low temperatures, this guy is likely to not be spontaneous because delta H is the most important. But as you start to increase that temperature, since you're multiplying by your temperature, your delta S term is becoming more and more important at higher temperatures. So it starts out non-spontaneous, but as you heat it up, it becomes. What's that? Okay. So Mercy, talk to us. Who's going to be next on the next one? Talk about the next one. I agree. And what about the temperature dependence? All right, we'll come back to it in a second, Owen, but Mercy, who? Murph. All right, Murph. All right, how about this one?
also negative.
It's all okay, but now give us more crunchy detail.
Okay.
This one is also maybe, but what about it? What about the temperature dependence on this one? And here's where we answer Owen's question, right? This one up here, what? Starts with a positive, right? At very, very low temperatures. And as you heat it up, it becomes negative. It becomes spontaneous. This one starts negative. Okay, so it starts as a spontaneous reaction, but
It's minus.
minus a negative. Oh, that's like plus a positive then, right? So what about temperature here? Starts out spontaneous as you. No.
I just said this.
Okay.
Um, I was just thinking of it as temperature times the.
That's correct.
Yeah, so when you asked me, and no temperature.
No, you're doing it right. Keep it, wait, temperature times, what does that tell us?
So then, that value would have to be, sorry, my wires.
I think this one's a hard one to put into words, maybe.
Like, I know what it is, because it's like, it's, negative minus, negative is, negative plus, whatever.
Right.
That's value that is.
So what determines whether the whole value is positive or negative?
If, that is more or less.
Right. Right. The scale of the delta S term versus the scale of the delta H term. So let me do the next slide, which is graphs, because I like to graph things. This might be one of the few places where y'all will agree with me that things are easier to see on a graph than a table. I don't know. I love my graphs. This is the same as this is the same slide as the last slide. It's filling in the table. Okay? In this case, down here, delta H is negative, and also delta S is positive, is what that says. Delta H negative, delta S positive. So as you increase temperature, right, you already had a negative delta H minus a positive value. This keeps going down. This is getting more and more spontaneous, but it always is spontaneous. Okay? Likewise, the top one, the red one, this guy starts out as non-spontaneous because it has a positive delta H, but as you increase the temperature, you're subtracting a negative, adding a positive, and so this becomes more and more non-spontaneous, right? The hard ones are the ones in between, the yellow, because this guy down here with a negative delta H might start out as spontaneous at low temperature, but as you increase temperature, look, it's approaching it, and there it's crossing over the zero line and becoming non-spontaneous. So this one's temperature dependent. So is the other one that starts off delta H positive and becomes spontaneous at high temperatures. Yes?
So positive, spontaneous, negative,
Yeah, that's correct. It's just wrapping your head around that and making sense of it instead of just trying to memorize. Okay? Yeah, it's good. Feel good with that? To calculate the temperature at which the spontaneity changes, what would you do? And look at my note in purple over there. This is an insight into my thinking. I might have written this as a question, right? Thinking, oh, this will be a nice easy one for them. And then I start grading it on the exam and I'm like, what the hell just happened? Right? So I write this question and I'm thinking, well, after what we just did, this is obvious, right, Ashley? Is this obvious? No? Is it obvious, Kira? See, this is that math thing, Kelsey. I think this is the math thing that I look at this and I'm like, oh, well, yeah, it's obvious, right? Because where's spontaneity happen? What value would you say the spontaneity happens at? Yeah, it's delta 0 for what?
They're decreasing.
So my equation is delta G equals delta H minus T delta F, right? He says 0. What do you want me to do with that 0? Keep it clean.
Looking for delta G.
Yes.
So we're
Now what?
looking for delta H. Equal this. That switches. Awesome.
Guys, what the temperature there?
Oh, you want the truck zone? No. So just a better.
The T in kelvins, at which this reaction changes from spontaneous to non-spontaneous is make sense?
Yeah.
Yeah, this is one of those that I would have thought, oh yeah, that's gonna be easy. Makes sense? Okay. Math ruins it. Back to our standard conditions idea. All right, purple arrow up there. When we put that little superscript 0 up there, okay, that indicates that it is the delta G for the reaction at standard conditions. Okay, and the conditions are not going to stay standard. But to do it, you should be able to calculate the delta G as the delta H at standard conditions minus temperature times the delta S at standard conditions. Okay, make sense? Please be careful. I do not know why this is the case. Anybody still have open that table where we got the values from? All you still have that open? Look at the top and look at the units. What are the units for delta H?
Yes,
Kilojoules. What are the units for delta G? Kilojoules. What are the units for delta S? Joules. Okay. Okay, y'all. I'm sorry that they do that, but they do. Almost always. The delta G and the delta H are in kilojoules, and the delta S is in joules, and I always see somebody screw it up by treating them all as kilojoules or treating them all as joules. So please be very careful. Make sure that you make your units. Right? I think this would be so much easier if we just listed the delta S's as 0 dot something instead of putting it in joules, right? Although that said, you should be developing a proficiency now in looking at units and converting. So I guess, yes, I don't prefer. So either way that you prefer, okay? I think that if Allison were asking me that question, we were studying for PChem, I would tell her joules, because you're going to convert so many things energy-wise. But if Murph were asking me that question, we're studying for compliance, I would tell him kilojoules, just because you're just going to do most of your stuff in kilojoules in that course. Okay, but yeah, whichever one you prefer, just know what you're doing. Does that make sense? And if you put 25 kilojoules or 25,000 joules, those are the same answer. Okay, both are correct if that's the correct answer. Make sense? Well, okay. So let's do a reaction then. Let's look at, remember I had used the hydrogen gas example early on, right? Talking about it being spontaneous. Well, let's see if we get a negative delta G out of this thing. How do we calculate delta G then? From a table? Given a table. How would I calculate my delta G for the reaction? Okay, good. Which could be your overall math for it. Delta G reaction equals
Delta G, it's a G products.
products minus reactants. Okay? All right, cool. Then what do I want to do here? What are my products? Yeah. What's my value? I don't know why your book does this. Does it still, the appendix still have delta H, then delta G, then delta S? Is that the order it lists them in? Also, I hate that table because it's not my Excel where it reads the top. You have to always scroll back to the top to see which column you're on, right? But it's a weird order. I would put delta G, delta H, and delta S because that's how the formula works. Delta G equals delta H minus delta. But they did. All right, so I want which value here for my water? What number value do I want? For my water. Negative 237.1 what? Kilojoules per mole. Okay? What value do I want for my reactants then, for my H2? Oh, 0. What about for my O2? All right, y'all. Back a long, long time ago, I told you that sometimes there was a nice reason for balancing your equations using fractions. Here's why. Because when we've got oxygen here, right, we're going to have to multiply our coefficient times 0. So it doesn't matter. So it's better to balance my equation so that the delta G of this reaction is just negative 237.1 kilojoules. Does that make sense? That's why I tend to balance my reactions a lot of times with fractions, because well, it just works out. You don't have to worry about it. You're already in terms of the reactant that you're looking at. Okay? Apparently I get it from a different spot, 237.2. But okay, within, sorry, I didn't mean for that to be confused. I probably got that off of a different thing. This horrible looking formula just says that you sum up your products and you subtract the sum of your reactants. But this equation right here does remind you to multiply by coefficients. Okay? So if I've got M A reactants, I need to multiply the delta G value by the M, by the coefficient. Yes?
This was just the sigma equations.
I agree, it is that. It's just being more precise with saying use the coefficients also. Okay. And this is why the zeros. The delta G formation for any element in its most stable form at standard conditions is defined as 0. Okay? Makes sense? Is it really 0? Probably not. We just defined it as. It has a 0 somewhere, and this is what we chose. So far, so good, y'all? Feeling okay with this? Okay, good, good. Alexis? Good? Okay. The reason I'm asking here is because I wanted to solidify this while we're here. Now, what does this little superscript 0 mean? At standard conditions. My next slide, we're going to go past standard conditions, okay? Because to be honest, you're working in chemistry, you're usually not working in PhD, right? Kind of things. Also, you got hydrogen involved, which we're going to have in the next unit, right? You'll want all your gas pressures, in this case, hydrogen gas, at 1 atmosphere pressure. So let's think about an experiment that we're going to do in electrochemistry. Electro means electricity, right? So we're going to have electricity around, right? And we're going to have a pH 0 beaker bubbling 1 atmosphere pressure hydrogen gas through it with electricity. What could go wrong? Yeah, okay. Yeah. So your reactions won't always be at standard conditions. We need a way to figure out our delta G anyway, even if our reaction is not at standard conditions. And that's where this guy comes in. So now, if the delta G superscript 0 means 1 bar pressure, 1 molar concentration, 25 C, now I can define a more general delta G of any reaction. Or not any. Any given constant temperature and pressure. Well, no, given constant pressure at least. Any reaction is the standard delta G that we get off the table. Okay, this is the piece that comes from the table. Delta G naught. The word I'm saying there, naught, is NaUGHT. It's Old English for 0. Okay, so the delta G naught is plus R. Y'all remember an R from anywhere? Ideal gas constant, that R, times temperature, in kelvins, of course, times the natural log of Q. Uh-oh. What was Q back in unit 2? Exam 2? What do we use Q for? Reaction quotients. Okay, so the product of all of the concentrations of your products, that's enough. Okay, multiply the concentrations of all your products together, divide by the product of all your reactant concentrations. Struggling with product means different things there. But okay, so LNQ, natural log of the reaction quotient. Oh, be careful with this too. A lot of times we use another value for R. Remember that R is R. It's just that here we're going to probably want it in the PChem version. So it's going to be 8.314 joules per mole K. It's still R. It's just that it comes out numerically as 8.314 when we're using these units to express it. Okay? Yes?
We need to have the other R.
I always would, just in case. And I don't want you memorizing R's, so if you run into a situation where like, oh God, if I only had R, I could do this. Okay. Well, now wait a minute. If delta G is negative, what do we say about our reaction? And if delta G is positive, what do we say? Non-spontaneous, in fact, is backwards. It would be spontaneous the other direction. And what if delta G is 0? It is at equilibrium. So some colleges teach this course in a different order, such that they do this early on in Gen Chem 1. Then, when you get to equilibrium, you can say, hey, we can just define equilibrium as where the delta G is zero. In fact, that is the definition of equilibrium, is when the delta G of the reaction is zero. Now, it's not, I am not saying delta G naught. That's probably not going to be zero, because you're going to get it from the table and it's going to have a value. But plus RTL and Q, that's the key, okay? And so when that zeroes out, you're going to get equilibrium. So let's think about that. Let me put that up here. What are we saying here? Equilibrium is defined as what? Equilibrium is defined as what? Delta G equal Z. But also, we now have an equation form for delta G of what? Marcy, what equation do you want to use to calculate it? This does not have a superscript. So what would I want to calculate it as? Delta G naught.
Plus RT, hash log.
So far, so good? Or I could say, well, wait a minute, wait. We're defining this as equilibrium, right? At equilibrium, Q gets replaced with K. Let's solve for K. What would you do to solve for K here? Let's do a step at a time. So what do you want to do first?
Drag.
All right, so I'm going to subtract delta G from both sides. Well, delta G naught, right? Because delta G is zero. I'm going to subtract delta G naught from both sides, right? These cancel, leaving me RT ln. Okay. Y'all see where I'm at right now? Alexis, what would you do next? By what? Oh, you're in algebra class, algebra test time. Yeah, divide something. What would you like to divide, lady?
Wait, what are we trying to solve for, right? So
Yep. RT. So negative delta G now, okay, 9 divided by RT leaves ln K. Sydney. I don't want ln K. I don't want ln K. I just want K. How do I get K? How do I unlog something?
something raised.
Yeah. Oh, wait, this one's not log base 10 like our pH was, right? This is Ln. What does that mean? It's what? Euler constant, which is spelled with an E. All right. So E, raise E to both sides. It gets rid of the Ln part. You know what? I'm going to put the E in blue, because that's kind of what we're doing. So E raised to this. Negative delta G naught over RT is equal to E raised to the natural log K. What's that, Kira? So you got E raised to the ln K. Leaving. Makes sense? This is how we do it. Yes, sir?
This E in natural will show up so much.
Well, remember, Euler's number is not invented, it's discovered, right? Really, if you could define this in a lot of other terms, you could define it in a base 10 system. You could define it in a base 2 system. would have probably made our science better if we'd done all this in a phase 2 system, right? Certainly the computers would make it better, right? But we didn't. So why is Euler's number special? You remember that, Douglas? Yeah, sort of. Where's that going with? What's the derivative of e to the x? Derivative with respect to x, v to the x is yes. That's fine. Because don't worry about it. Huh? Yes, it is. Yep. Yep. Yeah, we're never going to be here to help you, but but I'll be just out to Lafayette. All right. Sorry, I had to pronounce that. Come on, in Dade County, you can be throwing rocks at the glass house. Okay. Y'all got some stuff too. Okay. What are some of y'all? What are some of y'all's weird pronunciations up there? But there are.
Fail.
Yeah.
Okay. All right. Throwing rocks, glass house.
We're talking about cities in the beginning, we always go left by that. We're talking about someone that's so close to circle.
Yeah. Yeah, a friend of mine was from New Orleans, and we had and I told him to play it, like, what do you say? Oh, Drew, it's gonna hurt you. What I was trying to say here. Yeah. All right, so this is what we just did right here. Right? So we worked through it step by step, but it's all right here on the slide as negative delta G naught equals negative RTL. Okay? Yes? Make some sense?
What's the delta G like?
This is the delta G for the reaction at standard conditions. So practically, this is the delta G that we're going to get from the table in the back of the book. So when we do products from the back of the book minus reactants from the back of the book, this delta G naught is the one we're going to get, not what's actually going on in our beaker. To get the one actually in our beaker, we need to do that easy. And this discussion holds for all these different Ks that we did back in Unit 2. The concentration-based equilibrium constant, pressure-based equilibrium constant, the acid-base, Ka and Kb, works for those two. The Kw for water, the solubility product, the formation constants, that one's going to come up for you, Cindy, later. And this one, Kd, if you do environmental work, that one's super important. And that's the, really we call it absorption coefficient. I don't know what D, what the D is. I don't remember, but it's absorption coefficient, how much of your pollutant is attached to one thing versus free in water. And another important thing to realize. Now wait, if a reaction has a positive delta G, we say what about it? Non-spontaneous. So I'm going to make a statement here. Ready? So Carson, a reaction with positive delta G then never happens. Is that correct? Probably false, because of the way I asked it. Okay, biologists, is ATP to ADP, or is ADP to ATP likely spontaneous? Which one of those do you think is spontaneous? You have ADP and PI in a beaker, do they naturally form ATP? Or if you have ATP in a beaker, does it naturally fall apart into ADP and PI? Which one of those is natural in biology? ATP falls apart, right? Okay, so Carson, another way to phrase my question then would be, well then since ADP to ATP is a non-spontaneous reaction, then that never occurs. That's not true. It occurs, but it's non-spontaneous. How do non-spontaneous reactions occur? We staple them to a bigger spontaneous reaction. It's called coupled reactions. Coupled reaction thermodynamics is how you get unspontaneous things to happen, right? That's how the mitochondria are the powerhouse of the cell. It's how they create the ATPs for us, is by coupling to another reaction, which is pretty complex, which other reaction they're doing. Reductive or oxidative phosphorylation. They couple it to another reaction so that they can cause it to happen. Or in autotrophs, they couple it to just getting photons from the sun, right? In chloroplasts, and that's how they cause reactions to happen. Because you have something that applies the energy to it, something else that is bigger, spontaneous, to make your smaller, non-spontaneous reaction run in the presence of the other. Because you can do a total reaction, which is equal to reaction 1 plus reaction 2. And still get an overall negative delta G for the universe. So the universe is happy, but in our smaller sun, we can make a little bit of ATP. Okay? Oh, and then that comes down to that this is what I started with, right? So looking at this now, let's get to the top. Let's just look at this. This is ADP. Chemical form, right? I know in biology I'll usually just say ADP go, right? But this is actually the chemical, right? And so you can actually staple it together and make a delta G positive 31 kilojoules per mole. Here's that was a protein synthesis. Here's ADP and here's the ATP. These are the 3 phosphates, making it triphosphate. Those are your 3 phosphates on there. So that is non-spontaneous, right? So you have to couple some other reaction to that to make it go. And there's apparently an argument about whether or not this works. So let's say you want to build a biologic unit. Okay, Kara, you want to build new protein, right? So if you want to build new protein, that's that top reaction, the alanine to glycine. It's a very simple version. But look at the delta G, what does it tell you? You're taking alanine to a glycine and making adenoglycine, okay? Adenoglycine. What's my delta G? What's that tell you? Non-spontaneous. How do you do that? Take this guy. Bottom reaction. Flip it around. So then, if you flip it around, it's negative 31 kilojoules. Staple it to that one, you get a net 2 kilojoules. There makes it happen. Does that make sense? Yes? Okay. Yeah. I have not written your homework for tonight yet. I'll have to do that. It'll drop sometime soon. It'll be, that's not Tuesday night. When does it do? Sunday night? Is that right? Whatever night it is. And then go ahead and read chapter 17. I hope I got that right. Is that right? Chapter 17, is that electrochemistry? Whichever one is electrochemistry. Read electrochemistry for next week. I'll see you on Monday. Remember, we do not have lab on Monday. We are done with our labs. That's right.